In the previous two videos, you learned that if we have two gases that are at the same temperature and pressure, then they will have the exact same volume. And again, that is completely regardless of how large the particles are or what gas it is. We also learned that if we have 1 mole of any gas, again, regardless of what it is, it would have a volume of 22.4 liters. All right, in this particular part, as we approach gas stoichiometry, is that we need to understand that if we have a chemical reaction, and they're not just two gases just kind of, floating around doing their thing, but now they're actually involved in a chemical reaction. So now they're tied together and they're changing. They're being consumed, they're being converted, they're being produced. There's, again, a chemical reaction occurring. Well, if that is the case, and those gases in that chemical reaction are at the same temperature and pressure, then there's a very easy way for us to convert from one to the other, and that is basically to use the mole ratio. Now, to use the mole ratio, again, is going to be basically like a single mole to mole step back in good old stoichiometry. And that's basically correct. Because again, if we have two gases tied together in the same chemical reaction, then we could use that mole ratio because that, again, is the relationship. That's what a chemical reaction shows us, is the relationship between the molecules in that reaction. Now, again, this only works with gases. So do not try this if it's a solid. You'll notice all of these here are gases. Again, that is not a coincidence. That is a must. Okay, all that being said, let's go ahead and start with our first example. What we have here is we're going to calculate the volume or liters of ammonia produced when 5.5 liters of hydrogen reacts with an excess of nitrogen. Remember, an excess of something means it doesn't matter. It is not going to be a limiting reactant, so it's not really important to us. What I need to do now is balance my reaction. So I notice that my hydrogens are 2 and 3. To get them to be the same number, I need to get this to be 6, and I need to get that H to be 6. That also balances out my ends. So now we are ready to start. I'm going to begin with, again, the only number we have to start with, which is 5.5 liters of hydrogen. I'm going to move my liters of hydrogen down to the bottom. Again, it reacts with excess nitrogen, but that doesn't matter to me. I'm going to look for liters of ammonia. Ammonia is NH3. You guys can figure that out by the process of elimination. All right, then that will give us, in liters of NH3. So to do this part, again, just like a mole to mole, I'm going to use the molar ratio. On the bottom, I have H2. Again, there it is. That's a 3. On the top, NH3, there that is, and it's a 2. Knowing that, I'm going to go ahead and pick up my calculator. I'm going to do 5, help if I turn it on, 5.5 times 2 divided by 3. That gets me my final answer of 3.66, repeating, so I'm going to round that up to a 7, liters of ammonia. So again, they are not the same because, again, there's a chemical reaction. The hydrogen is being consumed. The ammonia is being produced. Therefore, it's not going to be equal. So because, again, there's a change going on here, a chemical change. All right, for our first problem, which we're calling number 1, we have 10 liters of oxygen. And we are trying to, again, we have excess hydrogen, so I don't really care about that. And we are trying to calculate the volume of water vapor. So I'm going to go ahead and balance my chemical equation. My H's are balanced, my O's are not. Now my O's are, but my H's are not, so fixed. There we go. So I'm going to go ahead and go back to my problem, put liters of O2 down here. We're looking for liters or volume of water vapor. So I'm going to use my balanced chemical equation to convert. On the bottom, O2, again, it's going to be 1. On the top, we have water. There it is. It's going to be 2. So liters will cancel out, and I will be left with 20.0 liters of water. Now, that's a calculation I can actually do in my head and be confident. Now, what's confusing about this example is that they tell us that it was reacted at 1.2 atmospheres and 25 degrees Celsius. Now, it may seem like we have to do ideal gas law because we have a pressure, we have a temperature, we have R, of course, that's given, and a volume. But this is not going to be an ideal gas law. because we have no moles and we don't need moles. Secondly, it's not going to be a Dalton's law, even though Dalton's law, when things are captured over water, we have a temperature and a pressure, and you might be thinking, oh, 25 degrees Celsius, I need to convert that into millimeters of mercury using my Dalton's law partial pressure water vapor table. That's also not the case because we already have the answer. It says calculate the volume of water vapor. Okay, we're not looking for pressure. We don't need Dalton's law because we're not looking for a pressure of water. We're looking for just a volume of water. And Dalton's law has nothing to do with volume, just pressures. Therefore, despite the extra information about the pressure and the temperature, those, again, don't really mean anything to us in this particular problem. So our answer is, in fact, just 20 liters of water vapor. That's it. So that problem is a little confusing in that they gave us extra information, which really wasn't necessary. All right, let's move on to number 2. Number 2, I'm gonna go ahead and balance my equation first this time, like I like to do, but I didn't previously. So my carbons are balanced, next my H's, oops, oh my gosh. Let's try that again. My H's are now balanced, and then my O's are last. So here I have 2 O's on the right side. I have 2 more O's, that gives me 4. So now it's balanced. I'm going to put 1s in so I know that it is finished. Okay, that's the combustion of methane. So what we're going to start with again is 15.5 liters because that's the only thing we have to start with. We're going to go ahead and convert out of liters of CH4. What we want to know is the volume of carbon dioxide, This will cancel, and we'll be left with some liters of carbon dioxide. Okay, again, you guys know this comes from the balanced chemical equation, CH4 on the bottom. There it is 1. CO2 on the top. Okay, it's also 1. Therefore, not surprisingly, my answer will remain the same. 15.5 liters of carbon dioxide gas would be produced from 15.5 liters of methane once it's combusted. All right, number 3. What we have here again is calculate the volume of nitrogen needed to produce 25.5 grams of ammonia. Uh-oh, they're giving us grams. That's a little bit different. I'm going to go ahead and balance my equation. I have 3 hydrogens on the right, 2 on the left, so I need them both to be 6. There we go. And that nicely fixed my nitrogens at the same time. So what I'm going to do is I'm going to take my 24.5 grams of ammonia. I don't need grams. I need, wow, actually I need liters. So grams, I'm going to put grams down here. I need to go through moles. Again, this is going to tie back into some previous videos. That will cancel out grams. Now, we don't need grams, we need liters. So I'm going to put moles of NH3. Then I'm going to put liters of NH3 because, again, we do know the conversion between liters and moles. For any gas, for every 1 mole, it is 22.4 liters. Then on the first conversion factor for every 1 mole, this comes from the periodic table. Let me go ahead and calculate this real quick. 1.008 times 3 plus the mass of nitrogen, which is 14.007. The mass of ammonia from the periodic table, called molar mass, is 17.031. So when I get this, it's going to be, my answer will be in liters of ammonia. And we'll finally be able to do the conversion into volume of nitrogen. So 24.5 times 1 times 22.4 divided by 17.031 divided by 1. My volume of ammonia is 32.224. Okay, then I'm going to take that number and I'm going to convert 32.224 liters of ammonia out of liters of ammonia. And ooh, that's a funky 3. And then I'm going to go into volume of nitrogen, which is what they want us to solve for. Okay, again, you guys know what's coming up. On the bottom, NH3, it will be 2. On the top, N2, it will be 1. So ultimately, it's just going to be the answer of liters of ammonia divided by 2. So 32.224 divided by 2. My final answer for liters of nitrogen, according to the equation that we were provided, is 16.112 liters of nitrogen. So there we go. So that one was a little bit more challenging in that they gave us the wrong unit to start with. They gave us grams. So I had to go from grams into moles, moles into liters. Once I had that, I could finally do what we had been doing on the previous examples, which is converting liters of ammonia into liters of nitrogen, again, using the chemical reaction provided to us. Okay. We have one more, so let's go ahead and do number 4. All right, so number 4, what we have here is we're to calculate the volume of chlorine gas needed to produce 75.3 grams of hydrogen chloride in a synthesis reaction at STP. Ooh, okay, so they're just trying to make this a little harder for us, aren't they? So we're going to have a synthesis reaction of chlorine gas to produce hydrogen chloride gas. Again, I'm going to put gas because, again, this does not work unless it's a gas. So this has to be H2 gas. Yeah, that has to be by the process of elimination. That must be hydrogen gas and chlorine gas reacting to make hydrogen chloride gas. Again, that would be hydrochloric acid if it was aqueous, but it's not, so it's a gas. Again, you'll learn more about that later. So to balance this, that couldn't be much easier. It's just a 1 to 1 to 2. So now that we have our chemical reaction balanced, I'm going to go ahead and go back to my numbers. What we are given to start with is 75.3 grams of HCl, which again is a gaseous form, so it's hydrogen chloride. Okay, I need to convert out of grams of HCl and into moles of HCl because really that's the only thing you can do. Cancel, cancel. All right, then we're going to go in from out of moles. This is again similar to number 3, HCl into liters of HCl. That will cancel. And we'll be left with liters of HCl. All right, when I have moles on top of grams, of course, my mole is always going to be 1. My grams comes from the periodic table. It's about 36. 35.453 plus 1.008 gives me 36.461. And then over here on the right side, for every 1 mole is always 22.4 liters. Again, that is a constant, regardless of the gas that we're talking about. So when I calculate this, I'm going to put 75.3 times 1 times 22.4 divided by 36.461 divided by 1 equals 46.261 liters of hydrogen chloride. Now, again, that sounds like a nice, good answer, but that's not what they want. They want us to calculate the volume of chlorine gas. So I'm going to take that answer and I'm going to go ahead and move on to the next step. I'm just going to go ahead and move directly into it because basically for lack of space. And I'm going to cancel liters of hydrogen chloride and go into volume of chlorine gas. Again, this is from the balanced chemical equation. On the bottom, we have HCl, it's 2. And on the top, we have chlorine, it's 1. So again, my answer is going to be basically whatever my previous answer was divided by 2, because that's how they're related in the chemical reaction. 46.261 divided by 2 is going to be 23.131. That would be liters of chlorine gas. So there we go. So again, that was very similar to the previous example. The only thing is that we had to come up with the balanced chemical equation ourselves. All right, guys, again, this, like I said, this is very reminiscent of a mole to mole. It's just, again, if they are tied together in a chemical reaction, then we know the relationship and we could just use the molar ratio. Again, as always, guys, thanks for watching.